What's up guys, my name is Cherno. Welcome back to remaking my first game in C++. Very exciting series. So last time we ended with a bit of a cliffhanger. We had this beautiful situation of random pixels. However, they were blurry. And they were blurry because we were using linear sampling when we actually drew them onto the screen in some form or another. I think we spent like a good 5 minutes, maybe even a good 1 minute trying to debug this, and I decided I'd leave it for today, so that's what we're going to do. We're going to dive in, take a look at how I approach an issue like this. We're not going to just like cut to the solution and that's it. I'm going to hopefully try and show the journey, you know, because life's about the journey, not about the destination. So from what we concluded kind of last time, if we go to, so we're using Walnut, obviously. Walnut uses ImGUI, that's how we draw this stuff. But Walnut also uses Vulkan to do the actual kind of image drawing. So there's a few kind of moving parts here. What we know though is we make a Walnut image, obviously, and we draw it here using ImGUI image, and we take the descriptor set from the image. Now there's probably going to be a lot of Vulkan terminology here. I'm going to try my best to explain this. This series, by the way, I didn't really kind of mention the target audience for this. I mean, not that I even get to really control the target audience, but in my mind the target audience is like beginner to intermediate for this series, right? I mean, we're remaking my first game, so there's clearly nothing too complicated here. So whilst there will be some advanced things here, and as I mentioned at the very end of this series, we're probably going to Vulkanize this whole thing, and that could be advanced if you have never kind of done graphics programming or Vulkan before. In general, I'm going to try and kind of take it slow and explain things, and if you guys have questions, please feel free to leave a comment, and I'll try and like actually address the comments every episode. So we make a Walnut image. This is the constructor we're using, so we take in data, we allocate memory for it, which will actually allocate memory on the GPU for it. But the way that like GPU rendering works is when you have an image to render, you don't just like render it by like reading the pixels and then just like copying them into a buffer. The reason why you don't do this, or why, well, you definitely can do this, just to be clear, but the reason why that's usually not how texturing works is because if you picture like a 3D scene, this is my little drawing of a 3D scene. Maybe I'll do it down here so it doesn't conflict with the face cam. So if we have this like 3D scene here and we have like, I don't know, a cube, right, that we've decided is going to be like somewhat textured with something. Pretend this is like a first person camera and we're moving around this scene and we're like, you know, looking at it from different angles, where we're moving closer towards it, we're moving further away from it. You can kind of start to piece together the fact that like these pixels that we read from just a 2D flat image texture, the way they kind of get, you know, copied onto our 2D display eventually, like the window on our computer that is actually rendering these 3D graphics, you know, at the end of the day, that's obviously 2D. So the way that kind of projection happens is kind of all over the place, meaning that like, you know, if you look at it from like an oblique angle or whatever, you might see like something like that, right? I'm looking at it like kind of side on. If you look at it, if you go like really close to it so that it fills the screen, it might be like this big. If you're very far away, it might be this big. There are all these ways that this can actually appear on your screen in the end result. And so because of that, it's not as straightforward as just copying like the pixels from the texture onto the screen, because there are so many different ways you could do that, depending on if you're making that texture larger than it actually is, if you're making it smaller, like whatever, right? And so one of the common ways that we get to define that process, which happens, by the way, automatically on the GPU, we have something called a sampler. And a sampler basically governs how a texture is sampled. And a sampler doesn't just include like filtering, meaning what happens if you need to magnify the texture or minify the texture. It also governs something called wrapping, which is basically what happens if you decide to use a texture coordinate that is outside of that 0 to 1 range. And again, now we're getting into texture coordinates. I don't really want to go down that route. There's a bunch of other things that samplers can control as well, like LODs or like which maps are used and all that stuff. We're not going to get too much into it. Just focus for now on the fact that a sampler, we use that, or we can use that to kind of determine what happens if we decide to render the texture larger than the source kind of material or smaller than the source material. And that's actually what is happening at the moment. We see that we're actually trying to draw this image at a scale, and this image scale is 3. So we're actually scaling up the image by 3. The actual texture that we draw, that kind of random, all of those random pixels, they're this big. But when we actually render them on the screen, they're this big. So clearly we need to kind of scale this up to fill this area. And so if every pixel is suddenly becoming, you know, 3 in each dimension, right? So this is like the worst diagram ever, but now it's 9, right? Every pixel has literally become 9. you know, what happens to all these other pixels? Here's my original pixel, beautiful, it's this color, right? But what do I do with all of these guys? How do I kind of expand this pixel to fill up the area of 9 pixels? Well, one of the ways I could do that is I could take this kind of green pixel and be like, well, you know, these kind of belong to this pixel. Like, this is like the nearest kind of source pixel, so why don't I go ahead and just make them all green? That's pretty straightforward, and what you've basically done is you've kind of enlarged the pixels here. You've just made the pixels really big. The 1 pixel now takes up an area of 9 pixels. However, you could also look at this kind of in a context. You know that next to it, you have another pixel, obviously. We have an image made up of many pixels, and this pixel is red. So why don't we, in an effort to try and make this kind of magnification smoother, what we could do is we could kind of decide to blend these two together. So for these pixels that are kind of nearby, let's, I don't know, make them kind of like orangey, or like, I guess yellow would be more correct, right? So we can kind of make these a little bit more yellow. We're kind of blending these together. And so what that does is it obviously doesn't create a very sharp result, because now you're creating brand new colors that are never before seen, but it is kind of like, it makes sense to do that if you have like a literal image or a photograph and you want to upscale it. It makes sense to kind of try and blend things together. But if you're going for a really sharp pixelated look, you obviously want the other strategy, which is basically saying that, you know what, let's just keep these pixels intact, but just make them bigger. And this is something called nearest filtering, which we briefly discussed last episode, or point filtering. So typically DirectX calls it point filtering, and then Vulkan and OpenGL we call it nearest filtering. Same thing, it just means that we look to like the nearest pixel. And by the way, these are even like, these terms are even found in like Photoshop when you scale stuff up and down, like using transform, Control T. So it's not just exclusive to graphics APIs, but we are kind of talking about them now, so hence why I'm saying this. Whereas the other method of kind of, you know, the yellow method of kind of blending everything together, that's called linear filtering. And there's kind of different ways to do linear filtering. There's bilinear, there's trilinear, there's a bunch of different equations that can actually play a role here. But typically, talking about samplers, we can set them to be linear, which is this, or we can set them to be nearest, which is like, you know, just making the whole pixel that color. The best way I always describe nearest filtering is like Minecraft textures. They obviously remain very, very sharp. The pixels just look big. It looks pixelated, it looks big, but it's very, very sharp. There's no blurring going on there. Even though the actual source textures, if I remember correctly, are 16 by 16 pixels. So they're tiny, but they get scaled up onto like a block in Minecraft and they look very sharp. That's because they're being scaled up, they're being magnified using nearest or point filtering. Okay, so that's a bunch of the terminology out of the way. So what's going on here? Well, if we zoom in, we can see that these pixels are nowhere near sharp. Actually, if I've zoomed into this level, you can actually start to see each individual pixel. And you can see that each individual pixel here is a completely different color. No two pixels are the same color, right? Which is obviously very wrong, because when we actually drew this in the first place, we obviously set every pixel to be one color, right? A single color. We do that over here when we set each pixel to be a random uint. However, we've scaled it up by 3. So we would expect to see like 3 by 3 pixels being the same color, but we don't. And that's because that linear filtering is actually happening. Now, that would be normally easy to fix. Like, we'd go into our image and we'd look at what sampler we've actually created here, because that's, you know, presumably the sampler that's being used for this actual image. And if we take a look at the sampler, I'll just search for sampler. It's got to be somewhere in this file. Okay, so here it is. VK sampler create info. This is how we create a sampler in Vulkan. And you can see the magnification and minification filter is set to nearest. Now the mipmap mode is set to linear. I'm probably not going to talk too much about mipmaps today, but basically that just means that it doesn't really have anything to do with the way we sample the texture itself. It's how we kind of blend between mipmaps. So if we're kind of somewhere in between like MIP 0 and 1, maybe like MIP 0.5, because that is totally valid. You can kind of be between mipmaps. Do we snap to the nearest mipmap, which is what nearest would be, or do we kind of try and blend between them, which is what linear is? So that's fine, but we're not really dealing with mipmaps here at all. So even though the word linear does appear here, these two are actually what apply to a specific MIP being sampled. So they are in fact set to nearest. Here's a sampler we create. The sampler goes into the descriptor set, and that is the descriptor set that we actually use here. And a descriptor set, by the way, is kind of like, it's like a binding to a resource in Vulkan. At the end of the day, we're going to be using a shader, and we have like a GPU pipeline that's going to read this resource, and a descriptor set kind of just, or a descriptor, I should say, kind of specifies which kind of slot in our pipeline binds to which specific resource, such as a buffer or an image. So in this case, it's an image. You're basically specifying, if my shader draws an image, which specific image is it going to be for that draw call, and that's kind of what the descriptor sets up. So that descriptor is seen being used here into IMGUI image, and it kind of gets passed as this texture ID, which if we look at that, it's just a void pointer, so it's a 64-bit value. And similarly, a descriptor set is also just a non-dispatchable handle, which is just like a Vulkan handle, which also is, well, it's a pointer. I think there's a specific, it's really just a pointer. So it's going to be like a 64-bit integer, basically. So they're totally compatible. So all of that kind of makes sense, but why isn't it working? So the kind of problem that we come to almost immediately here is it's simply not using our sampler, because our sampler has been set to be nearest, not linear. And it looks like we are specifying our sampler. And in fact, if you go into, so inside Walnut, we have this IMGUI build file, which kind of does a Unity build of 2 CPP files. One of them is the Vulkan, one of them is the GLFW one. So these are specific kind of backends, as you can see, for IMGUI. If you look at the actual IMGUI project inside kind of Walnut's dependencies, you'll see there's nothing backend specific here. It just builds IMGUI, and then the client application, in this case Walnut, you can see this file is inside, you know, the Walnut project, that then specifies which backend you want to use. That just makes it a little bit more flexible so that you can kind of choose to build like different backends, different graphics APIs based on what you use, and this IMGUI isn't like restricted to build all of them or some of them, and we don't need to change configurations or anything like that. So basically, in this case, you can see this Vulkan CPP file contains all the Vulkan specific code. So this has got to contain obviously all the samplers. And then if we go to something called like render draw data, which I'm pretty familiar with IMGUI, so I just know it's there. This is actually what goes through that kind of, all of those draw kind of lists, the draw data. I don't know how deep I should get into how IMGUI works, but basically what IMGUI does is it collects this huge list of like data that needs to be drawn. So basically, whenever we execute any kind of like IMGUI begin, which creates like a new window, IMGUI image, which adds stuff to it, like whatever IMGUI stuff we kind of you know, call over here that actually does stuff, that draws stuff, that will just be added into like this list called a draw list. And then later, eventually, like at the end of the frame, when all of that has like concluded and it's time to actually draw it, it will go through that list and actually execute the draw calls and the draw commands. This is important because it lets us kind of batch things together. It means that we don't need like a draw call for everything. If we drew it immediately, that would not be anywhere near as good, and that would be quite limiting actually. So we can kind of go through these draw lists at the end of the day and actually draw the stuff we need to draw. Now, as part of drawing it, we bind descriptor sets, which is us kind of binding a set of descriptors which represent resources that we're actually using in that draw, and then we execute the actual draw call. So over here, when it does this, you can see what it does literally for this kind of font or user texture, which is what we're doing at the moment. We're drawing our own texture here. It's supposed to take the descriptor set, which is from the command, the texture ID. So if you remember, let me just keep this kind of open. And then if we go to IMGUI image, user texture ID, add image, and you can see that kind of basically will go push texture ID, that will go into that kind of texture ID slot that is inside like the command that we're actually like, I guess, trying to execute here. So if we go back here, that's what that's supposed to be. The command's texture ID is supposed to be this texture ID. That's where we kind of set it from. And then that descriptor set here. Now, if the size doesn't match for whatever reason, so if the size of IM texture ID is less than 64 bits, which it does not apply to us, but that means we don't like where IM texture ID somehow isn't 64 bits, so whatever, we don't really care about this branch at all. This is what happens. So this descriptor set gets bound. And what is that descriptor set? It's the set that contains our texture. So clearly it's supposed to be getting bound here. Like as far as we can tell from the code that's actually executing, our sampler, which is set to nearest filtering, is in fact bound. However, we see a different result. So what do we do at this point in time? Now, there is, from my personal experience, there are lots of other things that could be kind of the culprit here. But I'm going to pretend I don't really know that to show you how I would start kind of debugging something like this. And one of the best tools you can use is basically a graphics debugger, such as RenderDoc. Now, what RenderDoc is it's a tool that you can use to basically see what your GPU is kind of doing, or specifically what graphics API commands you have decided to execute, as well as inspect certain memory or textures that you have, right? And they also let you kind of look at every draw call individually and see like what's actually going on there. It's immensely helpful because instead of looking through your own kind of code, you can see exactly what is actually happening, as well as any parameters that are like the state that's currently set. Now, there are two tools that I use regularly for this when I'm like working on Hazel and I need like a serious kind of graphics debugger for a lot of the advanced features we use: RenderDoc and NVIDIA Nsight. I basically always run NVIDIA GPUs, so that's why I use Nsight a lot. We do have AMD GPUs as well in the office, of course, because we support them as well for Hazel. However, on my development machine, I always basically have NVIDIA. And just to kind of show you Nsight, I guess the latest version, Nsight looks very similar. You can kind of go quick launch and then set up like, you know, application executable, working directory, same kind of options as this. Now, lots of people always recommend RenderDoc because it's a little bit more kind of open source. It's not obviously specific to like NVIDIA like this, but I will just flat out say that Nsight is definitely better. This isn't really meant to be a deep dive on graphics debuggers. However, Nsight is much more detailed, especially if you have like at least a 20 series NVIDIA GPU, because then you get some much more kind of in-depth measurements and data. Like, for example, GPU trace profile is really good, but it only supports DirectX 12 and Vulkan, so that can be somewhat limiting if you're using something like OpenGL or DirectX 11. But anyway, the point is, I frequently alternate between the two of these, just because RenderDoc's a lot more lightweight, in my opinion. Like, it's less clunky, it's much more kind of straightforward and easier to see what you're doing. But Nsight provides much stronger tools, I guess. It gives you much more detail, and it basically works 99% of the time. Like, there have been many times where I've opened up RenderDoc and I've inspected my buffers and it's just incorrect. Like, the data is just wrong. It's just getting it wrong. Whereas in Nsight, the data shows up correctly. So that's why I kind of oscillate between the two. I'll usually try RenderDoc first, and if it doesn't give me what I need, or I know I need something more in-depth, then I'll go to Nsight. But just know that there are two options. Like, again, Nsight obviously only supports NVIDIA GPUs. However, there are multiple options. Like, every manufacturer will, like AMD obviously has their own tools as well that you can use. But RenderDoc is just kind of like a popular thing in between. Okay, so how do we set this up? Well, there's this launch application tab. It takes in an executable path, working directory, command line arguments, and that just lets us kind of launch our application. So we know that we built this into a particular directory. If we go into like, maybe it'll even be here in debug. Yeah, so here's the exe. You can see that's the first thing it loads. So I can just kind of copy the path from here, or you can obviously just go to like the output directory. So like over here, this is where it built the exe to. So I'm going to copy that path, paste it into here, add the genesis.exe at the end. Now it needs a working directory. Now the working directory in our case is not the same as the executable directory, which is what it's assuming. So we need to kind of go back to what our working directory is. And it's going to basically be this Genesis directory that has our VCX proj, because when we run it through Visual Studio, and this probably doesn't matter, to be honest, at this point in time. I don't think we have any resources to load that are relative to the working directory. But if you go to your like property pages here and you go to debugging, you can see this is just, I decided to turn my scaling up to 150% just so it would be easier to see like on a small display. But of course, Windows still hasn't like figured out display scaling. You can see the working directory is project directory. So therefore, when you run it through the debugger in Visual Studio, this is the working directory. So sometimes when you kind of have files relative to your working directory, which is the project directory, which is this guy over here, then you need to also make sure that you kind of launch that. Yeah, like for example, I guess ImGUI is really the ImGUI INI file, which is like the layout file for our ImGUI thing, is really the only file we actually load here. But we'll paste in that directory, no command line arguments, we'll just hit launch, and then it's going to launch this. You see we have like a little capturing Vulkan, we have like some text over here from RenderDoc. If we just hit F12 now, as it says, to capture, we get a capture saved. And if we switch back here, we have that capture here. Now we can either close it or keep it running. And if we close it, it'll automatically load that capture. And now we have the capture. So what this is kind of that entire frame, everything that went into that frame has now been captured. And if we go up here to this timeline, you can see if we kind of click over here to expand these little things, we have all of these different kind of events. And the events show up in the event browser over here. and you can see every single event kind of happens here. So if we wanted to see like every draw event, we could just type in like the word draw, and you can see if I type in draw here, we have like the 3 draw calls that happen for this frame. We can see them over here, and we can see how many indices happen in that draw as well. So pretty useful stuff. Again, much more useful usually if you're developing like complex 3D engines and you need to kind of debug various things that may have happened, but it can be useful for things like this as well. So you can see this is us. So what is this event? If we kind of clear this filter, it should show us. This is the VK command copy buffer to image. So this is us actually setting the data. You can see over here inside Genesis app.cpp, we every frame do image set data, and then what does that do? That does at the end here, it does, or over here, it records into a command buffer VK command copy buffer to image. So that's what's happening over here. VK command copy buffer to image. So these are the actual pixels, and you can see how nice and big and sharp they are. These are the actual pixels that get copied into that buffer. So they're obviously correct because no sampler is used here. This is just us copying data from our CPU to our GPU basically, and this is what it looks like. That's the data, right? So that's great. Then we submit that queue, sure, whatever. But then inside this color pass number 1, so this is just like, you can see over here in the timeline, it says this is just like a copy clear pass because we're just copying stuff. But then this is actually a color pass. This is actually an actual render pass. This is where IMGUI draws everything. So this seems to be like our clear color. And then over here, we do command draw indexed, and it doesn't look like we're really drawing much. This might actually just be the background for IMGUI because it's not quite black. It's like 0.05, so it's like a gray here. You can see the color here. By the way, if you just right click, it will actually sample pixels, and the pixels value will show up here, which can be very useful as well. So you can see that value is 0.05. By the way, I made a video about Bloom like a really long time ago. Year and a half ago maybe. I use RenderDoc there quite a lot to show how Unity's Bloom works. So I'll have that video linked up there. Check it out if you're interested in kind of how RenderDoc works in a bit more of a real context, I guess is what I'm trying to say. Because there's going to be like a light usage of it. So there's like the top bar being drawn. You can see we can scrub through here. And this is our texture being drawn. And if you look at it, yep, that is in fact incorrect. That's like kind of linearly sampled version. And then we have this kind of inputs over here. I might just try and lower it a bit so you can see. If we double click on this, you can see the input, this is the source data, and the output is this. So clearly the sample is happening at this exact draw call, which is right over here. And if we go into like resource inspector, is it resource inspector? Pipeline state, that's what I meant. Pipeline state, you can see that over here inside like the fragment shader, which is where that's being drawn, we have an image and sampler. And if we take a look at the sampler, there's a few interesting things here. First of all, you'll see the words immutable sampler. More on that later. But if we actually click on this sampler, it takes us to the resource inspector because a sampler is a resource, just like a texture. It's treated as a resource. And then we can actually see the resource initialization parameters, which is pretty cool. So we can see that how was this sampler created? It was created with VK create sampler. You can already see that it says linear, but we can actually expand this. And then you can see that if we expand create info as well, let me just scroll down a bit. I'll make this bigger. You can see that we actually can see like literally how this resource was created and all of its parameters, which is super useful. So there's our problem. We obviously, when we created the sampler for the image, what did it say? Nearest. This does not say nearest. It says linear, right? Everything else looks fine. I don't really care about anything else, but this is clearly wrong. So this is clearly a different sampler, which again can be difficult to track down, I guess, how exactly that happened, because as far as we're aware, when we looked at the code, it was using our sampler. We saw that. But the trick is in the fact that this says immutable sampler. What you can actually do in Vulkan is when you set up a descriptor set and it has a descriptor set layout, you can actually say that, you know what, screw the sampler as provided in the descriptor. Like, just don't worry about it. I'm going to provide my own immutable sampler, meaning my own kind of read-only, unchangeable sampler. That's what you're going to use. It's almost like an override. And so that has clearly happened when the pipeline has been created. Now, we could dig through IMGUI and we could try and find where that descriptor set layout happens, which is probably going to be in some kind of like pipeline creation code, right? However, I want to also draw your attention to this. This is the last video. And a lot of you probably think that I don't read my comments, but I do. And whilst doing so, I noticed that this guy, Sean Nolan, had pointed out that he had the exact same problem with IMGUI images. It's because IMGUI ignores the samples you provide, upgrading to the latest IMGUI solves it. So this is usually like the best scenario, right? If we know that we can just upgrade to a new version, we don't have to go in and dig through the IMGUI code. Why is that so bad? Because it means that when eventually changes do happen and we do want to update, we might have merge conflicts because we've kind of modified that like third-party library, and that, you know, if that can be avoided, it's a good thing to avoid it. And so what I did, because remember that technically speaking, the IMGUI that Walnut uses is actually my kind of fork of IMGUI that's on the docking branch. So what I did is I updated it like an hour ago, right before recording this video. I thought I'd update it. I'd see if that comment was like correct. What do you know? Nothing. Didn't work. So then I was like, well, either this Sean character's suspicious and we shouldn't trust him, or maybe it's because we're on the docking branch. So what I did was I just went to the kind of main repository here. This is the master branch. And then what you can do is you can just search, right? So I searched for sampler in this repository, and you can search through the commits. So if you click on commits, you can see that, hey, check this out. There's a commit which says do not set descriptor set layout binding immutable. It looks like exactly like what we're after. And you can see here that in the changelog it says fixed sampler passed to IMGUI Vulkan add texture not being honored. Okay, so that sampler not being honored. And how is it fixed? Here is the actual like diff of code. Inside this function called create device objects, it's very simple. Just remove the font sampler, which is apparently what was being set as the immutable sampler for this descriptor set layout binding, right? So by this line of code being here, by setting an immutable sampler into that descriptor set layout, we were overriding any samplers that were part of the descriptor set that we were actually setting in the command buffer. So this is present in the master branch and actually was only done about a month ago. And I guess it just has not been merged into the docking branch, which is what we're using. But of course, it's simple enough for us to just take this code. So what we'll do is we'll go to that create device objects function. Here's our font sampler being created, as you can see with linear. That's fine. That's what we want to use for fonts. However, for this guy, which is just our descriptor set layout that's used for like the entire pipeline, or like the main drawing pipeline, I guess, immutable sampler, you can see is being set to sampler, which is the font sampler. So what we can do is just basically just not do this. And if we don't do this, and we hit F5, look at that. We now have very sharp pixels. So that is basically the solution. A little sneaky immutable sampler was just set on the actual descriptor set layout. Fun indeed. Now, what would have happened if IMGUI didn't have the solution for this? Well, you can see that it says here that we have an immutable sampler. So really, it's just as simple as searching this file for the word immutable, which happens in a few different places, and really in 2 different places, and just like removing it so that we can set our own, or potentially changing this one to be nearest. I wouldn't change the font sampler to be nearest, but what I might have done maybe is I could have obviously created a new sampler, so another one of these that was set to nearest, call it like nearest sampler or something, and set that as like the kind of immutable sampler. But I would prefer not to do that, like especially because in this case, when you provide an image to IMGUI, it makes sense that the image dictates how it's sampled in this case, right? And that would be achieved in our case by just saying that, you know, we'll provide our own sampler, which lets us pick nearest or linear. I've gone ahead and just flat out changed image to be like always nearest, which is also wrong. You'd usually, like when you create the image, maybe you could specify some parameter that says this is the kind of filtering I want. Or maybe you could even have a separate abstraction for samplers that you create. Samplers can be a bit of a deep topic just because it makes sense to reuse samplers, so not for every image to have its own sampler, but to have samplers as a completely separate resource, since you can imagine like a game with thousands of textures, and they all want to be linearly sampled, right? Or they all want to be nearest sampled. So why would you provide 1,000 samplers? That's just a waste. But yeah, that's basically all I had planned for today. That didn't really turn out to be that quick, but hopefully it was like comprehensive and you guys enjoyed it. This video is also not sponsored, so if you want to hit the like button as consolation, that'd be good. I just made this video from the goodness of my heart. Next episode, we're probably going to, let's actually try and draw some stuff, right? So maybe we'll start on like the tile rendering or the screen class, basically from the Java version, because now that we have this kind of figured out, we can actually start, I think, drawing sprites, and that might be a good thing to do. Maybe I'll even watch my game programming series from like 2012 to see how that's done. But anyway, I'll see you guys in the next episode. Bye.